In this section, we will introduce statistics, the field of statistics, which is really the entire focus of this course. So we'll provide a formal definition. And then we'll spend most of our time in this section discussing the process of sampling. So here's the objectives that we will cover in this section. We will go over the process for constructing a simple random sample. We will talk about samples of convenience and determine specifically when samples of convenience are acceptable. We will describe and define some other sampling methods, specifically stratified sampling, cluster sampling, systematic sampling, and voluntary response sampling. And then finally, we'll wrap up by distinguishing and defining statistics and parameters and looking at the difference between those. So let's move into our first objective, which is how to construct a simple random sample. Before we talk about simple random sampling, I just want to define some terms. And specifically, I want to get us to the point of looking at a formal definition of statistics, so we have an understanding of what statistics is. To help us understand that, we could think of a real-world scenario that we're all familiar with, and that would be elections. In the months leading up to an election, we always see polls that are released by various media outlets. The purpose of these polls is to give us some idea or prediction about where the current standing of the election, right? So it would basically be a statement of, if the election were held today, we predict that this candidate would beat this candidate, right? Now, the polls are based off of data, specifically data that's obtained by surveying actual voters, right, within the population where the election is being held. Okay. Now, if you want a poll that is 100% reliable, right, completely reliable, that could only happen if you survey every single individual within an entire population. Now, populations tend to be very large. We're talking about millions, possibly hundreds of millions of individuals. And so it's almost never practical to survey every single individual within the population. And in reality, the polls that we see that are released before an election are pretty much never based off of an entire population. Rather, they're based off of a sample or a subset of individuals, right? Typically, this subset, which we refer to as a sample, it may be anywhere from a few hundred to maybe a few thousand individuals, but it's much, much, much smaller than the actual population. Okay? And so the actual data that is used to release the poll is based off of data that's obtained by surveying the individuals within this relatively small sample. Okay? The data is not based off of the entire population, but simply this sample. So the process of polling requires two major steps. First, the voter is to be polled. They must be selected and interviewed. And this is the way that pollsters collect information, right? So the information has to be collected. Then in the second step, the pollsters then have to analyze the information to make predictions, right? The actual prediction can only be made after an analysis of the data is made, right? So the data has to be collected and then it has to be analyzed. Those are the two critical steps. And the field of statistics is the field that gives us the tools to do this, okay? Provides the appropriate methods for collection, description, and analysis of information. So with that in mind, that leads us to, we can now kind of formally define a few terms. Statistics is the study of procedures for collecting, describing, and drawing conclusions from information. In order to collect information and draw conclusions, we do that by collecting data from a sample, right? So in statistics, typically, we are trying to understand some characteristics of a large population, right? A population is the entire collection of individuals about which information is sought. It's typically not practical to collect information on every single individual in the population. So instead, we focus on a smaller subset, which we call a sample, right? A sample is a subset of a population containing the individuals that are actually observed. Now, the tricky part here is that the sample is quite small as compared to the population, right? And so if we're not careful, if we're just basing our data analysis off of this small sample, if we're not careful, then we may end up with a situation where the results of our analysis do not reflect the larger population, right? And we want the information that we analyze to be reliable, okay? So in order for that to happen, we would like our sample to represent the population as closely as possible, right? In a political poll, ideally, we would like the proportions of voters in our sample that prefer each of the candidates to be the same as that of the population, right? So that would be the only way for the poll to make an accurate prediction. Unfortunately, there are no methods that can guarantee that a sample will represent the population well. That cannot be guaranteed. However, there are certain sampling methods that are better than other sampling methods. And if we use a good sampling method, then that increases the likelihood that our sample will be a good reflection of the population. It doesn't guarantee it, but it does make it more likely if we use a good sampling method. The most basic, and in most cases the best sampling method, is a method that's referred to as simple random sampling, okay? And to understand the nature of a simple random sample, we could think of a lottery. Let's imagine that 10,000 lottery tickets have been sold and that 5 winners are to be chosen, right? And we want to choose the winners in the fairest way possible, right? Well, the fairest way would be to do something like put all 10,000 tickets in like a big barrel or a drum, mix them up really good, thoroughly, right? And then just randomly reach in and randomly pull out 5 tickets, right? The idea here is that if you do this well, in a truly randomized way, then every single one of the 10,000 tickets has an equal chance of being selected, right? We try to eliminate bias as much as possible, right? We want every ticket to have the same likelihood of being selected, right? Or another way of looking at this is we could say that if you have 10,000 tickets and there are only 5 winners, right, there are a lot of different ways that 5 tickets could be selected out of a pool of 10,000 tickets, right? And if a method is truly a simple random sampling method, then it means that every sample of size 5, right, is equally likely to make up the sample of the 5 winners, right? Or more generically, we could define a simple random sample in this way. A simple random sample of size n is a sample chosen by a method in which each collection of n population items is equally likely to make up the sample, right? And the analogy that we looked at is that of a lottery, right? If we suppose that 10,000 lottery tickets are sold and 5 are drawn as the winning tickets, each collection of 5 tickets that can be formed is equally likely to comprise the group of 5 that is actually drawn, right? So that's officially how a simple random sample is defined, but it also really means that every individual within the population is equally likely to be selected to be a part of the sample, right? So the main thing is that we're not, there's nothing about the sampling method that skews the likelihood of selection towards certain individuals or away from other ones, right? It's just an equal opportunity, no bias way of selecting a sample. So typically in statistics, the best kind of sample is either a simple random sample or some variation of that. So let's consider some examples, right? Here's the first example. A physical education professor wants to study the physical fitness levels of 20,000 students enrolled at her university. She obtains a list of all 20,000 students, numbered from 1 to 20,000, and uses a computer random number generator to generate 100 random integers between 1 and 20,000, and then invites the 100 students corresponding to these numbers to participate in the study. Is this a simple random sample, right? If we look at the process described here, right? So basically, the population is the 20,000 students in the university, right? From that population, we're selecting a sample of size 100, right? We want every individual from that population to have an equal likelihood of being selected to be in that sample of 100, right? And the process being described here is, it is a completely randomized process, right? Because of the random number generator method. So yeah, this is a simple random sample, right? Because the idea here is that the students are all numbered from 1 to 20,000, right? And then the use of the random number generator, where we're just randomly generating 100 numbers between 1 and 20,000, right? Where any one of those numbers is equally likely to be generated, right? So this is a completely randomized process. So this is a great way of selecting a simple random sample, right? Since any group of 100 students would have been equally likely to have been chosen. Second example, the professor in the last example now wants to draw a sample of 50 students to fill out a questionnaire about which sports they play. The professor's 10 a.m. class has 50 students. She uses the first 20 minutes of class to have the students fill out the questionnaire. Is this a simple random sample? So if we look at the process involved in this polling, this sample collection process, it does not qualify as a simple random sample, right? Because for a simple random sample, basically every group of 50 students would have to have an equal chance of being selected as the sample, right? But that's not the case here, right? The only students in the population that have a chance of being selected are the specific 50 students in this one class. None of the other students in the 20,000 student population have a chance of being selected, right? So the method used here does not look like a lottery. It does not meet the criteria for a simple random sample. Okay. Let's move on to our next objective. Simple random sampling is really the simplest and, like we said, often the best method for collecting a sample. It's not the only method, however, and let's talk a little bit about a different sampling method, which we call samples of convenience. Basically, a sample of convenience is maybe utilized in certain cases where it's just difficult or impossible to draw a sample in a truly random way. In these cases, the best we can do is to sample the items by some convenient method, right? So we use some convenient method, but that method we use may not necessarily be a randomized method. So we define a sample of convenience is a sample that is not drawn by a well-defined random method. Okay. So to illustrate an example of what a sample of convenience might look like, let's say we have a construction engineer who has just received a shipment of 1,000 concrete blocks. The blocks have been delivered in a large pile. The engineer wishes to investigate the crushing strength of the blocks by measuring the strengths in a sample of 10 blocks. So we want to explain why it might be difficult to draw a simple random sample of blocks. Remember that a truly randomized process means that every single block in the entire pile would have to have an equal chance of being selected to be part of the sample, right? In reality, however, that's not going to be practical in this case because it would be really difficult to select blocks from the middle or the bottom of the pile, right? So most likely, if we're drawing a sample of 10 blocks, we're not going to use a truly randomized process, right? Because of the impracticality of removing blocks from the bottom of the pile. Instead, what we would do is we would simply select 10 blocks from the top of the pile as our sample, right? And we refer to that as a sample of convenience, right? Because really the only blocks eligible to be included in the sample are those on the top, not the ones in the center or the bottom. So we have to really be careful with samples of convenience, right? The main problem with samples of convenience is that they may differ systematically in some way from the population, right? So with regard to the concrete blocks, if the engineer is confident that the blocks on the top of the pile do not differ systematically in any important way from the rest, right, then which seems probably reasonable for a pile of blocks, right, then he can treat the sample of convenience as a simple random sample, right? But if for some reason it might be possible that the blocks in different parts of the pile may have been made differently, whether that's different batches of mix or different standards for some reason, then that could be concerning, right? The sample of 10 blocks from the top may not necessarily be a good representation of the entire pile of blocks. This gets even more tricky when the sample is people, right? A pile of concrete blocks will tend to exhibit a lot of uniformity, right? But when we're talking about people, there's always a lot of diversity, whether that's ethnic, age, income level, or whatever, right? An example of a sample of convenience of people, it might be to stand in front of a neighborhood store and survey the first 10 people that walk out or something like that, right? But if we're doing that to try to get opinions about, say, a statewide election, right, or even a county-wide election, there's a pretty good chance that the sample we obtain would not be a good representation of the population as a whole, right? Because it would really most likely be biased towards people of an individual neighborhood. So we really have to be careful about samples of convenience, right? So if it is reasonable to believe that no important systematic difference exists, then it is acceptable to treat the sample of convenience as if it were a simple random sample. But that's about the only case where a sample of convenience can really be trusted to give us accurate information about a population. All right, next objective, let's go over a few other sampling methods, specifically stratified sampling, cluster sampling, systematic sampling, and voluntary response sampling. Okay. what we'll see is that stratified cluster and cluster sampling specifically still utilize simple random sampling as part of the methodology, okay? But they're used for specific circumstances, such as trying to glean specific information about a population, maybe along demographic lines or something like that. Or in the case of cluster sampling, it makes it more practical when we have a large population that's spread out geographically. And then systematic sampling lends itself well to data that is organized in some way. So let's define each of these. In stratified random sampling, the population is divided up into groups. We call these groups strata, and then a simple random sample is drawn from within each stratum. So stratified sampling is useful when the strata differ from one another, but the individuals within a stratum tend to be alike. Okay. If we go back to the idea of election polling that we referred to at the beginning of this lecture, we'll often see polling data that's based off of the entire population, but then we might see specific data that's based, maybe divided up along gender lines, right? So we might have a population, a sample that was obtained just from the population of women, and then another poll that was obtained just from the population of men, right? So we get specific information about how men and women feel about an upcoming election. Or you might see polling that is specific to different income levels or ethnicities and things like that. So in those cases, those are examples of stratified sampling that are used to try to glean more specific information about a population. But then stratified sampling can also be used to guarantee that the proportions of our final sample match those of the population. Kind of like this example right here. A company has 800 full-time and 200 part-time employees. To draw a sample of 100 employees, a simple random sample of 80 full-time employees is selected, and a simple random sample of 20 part-time employees is selected, right? And then those, the 80 full-time and 20 part-time are combined together to give us an overall sample of size 100. And by utilizing stratified sampling, that guarantees that our final sample has the same proportions of full-time, part-time employees as the population, okay? So that's stratified sampling. Next, let's talk about cluster sampling. In cluster sampling, we're still utilizing simple random sampling, but instead of just sampling individuals, we are sampling groups of individuals, which we refer to as clusters. So cluster sampling is specifically most useful when the population is too large and spread out for simple random sampling to be feasible. It's oftentimes used by the government for large-scale government surveys of some sort. For example, estimating the unemployment rate. A government agency draws a simple random sample of households in a county. Someone then visits each household and asks how many adults live in the household and how many of them are unemployed. Right, so we're drawing a simple random sample of households, and so the households would be the clusters, okay? And then, this is a cluster sample because we're doing a simple random sample of clusters, right? So the households are the clusters, right? So on the left, we see that represents the population, right? But the population is the population of all the households. We select a simple random sample of households, and then somebody visits each of the households selected, right? And surveys the individual within each household. And if we're trying to understand unemployment rate, right, then the survey questions would basically would be used to try to determine how many adults in each household are employed and how many are unemployed, right? But the final sample would be based off of the individuals within the households that were selected. Okay, systematic sampling. This is used when you have items that are ordered in a specific way, maybe for items that are coming off of a assembly line, or if you have individuals who are maybe lined up single file or something like that, right? But basically, if your population items are ordered in some way, then with systematic sampling, it would be like selecting every kth item, whether that's every 5th item or every 10th item would be chosen to be included in the sample, right? So systematic sampling is sometimes used to sample products as they come off an assembly line in order to check that they meet quality standards. So that's a common application of systematic sampling. Here's an example. Let's say that automobiles are coming off an assembly line. It is decided to draw a systematic sample for a detailed check of the steering system. The starting point will be the 3rd car, and then every 5th car after that will be sampled. Which cars will be sampled, right? So we start with car number 3, and then we take 3 and add 5, right, which gives us 8. So car number 8 would be sampled. Then we add 5 again, which gives us 13, right? So we would select car number 13, add 5 again, which gives us 18, and so on and so forth, right? So 23, 28, and so on, okay? So that would be a classic example of systematic sampling. Okay, finally, voluntary response samples. These are often used by the media to try to engage the audience. So for example, a radio announcer will invite people to call the station to say what they think, right? But they're not required to call. They're invited to, right? So their response is voluntary. If we are trying to do a rigorous study to understand characteristics of a population, we should pretty much never rely on voluntary response samples. Voluntary response samples are never going to be an accurate portrayal of the population for the following reasons. Typically, people who volunteer an opinion, they tend to have stronger opinions than is typical of the population. And then it's also been documented that people with negative opinions are often more likely to volunteer their response, right? So a voluntary response sample will tend to be biased towards those who have stronger opinions and more negative opinions. And so that kind of a sample, while it might make for some interesting sound bites, or a interesting to listen to talk show, it's not reliable for getting an accurate portrayal of the population at large. So that is what you have to be careful with those. Okay, we've gone over simple random sampling and then defined a few other sampling methods. It's worth mentioning that for the rest of this course, in general, if we refer to sampling, we mean simple random sampling. Unless it's specified otherwise, sampling in this course will be defined as simple random sampling, because in most statistical applications, that is the best sampling method to use for getting the best possible sample. So we will wrap up this section by defining a couple more terms. Okay. Specifically, we want to define a statistic. A statistic is a number that describes a sample, and a parameter is a number that describes a population. Okay. To illustrate a couple of examples of this, we'll present a couple of statements. and we want to determine which statement refers to a statistic and which one is a parameter, right? The first statement, 57% of the teachers at Central High School are female. The second statement, in a sample of 100 surgery patients who were given a new pain reliever, 78% of them reported significant pain relief. Both statements refer to a percentage, right? The first statement here, though, this is a parameter because the 57% is based off of the entire population of teachers in the school, right? It's based off of a population. In the second statement, this is a statistic because the 78% number is based off of a sample of 100 patients, right? It's not based off of the entire population, but a subset or a sample. We'll be kind of referring back to these concepts throughout the class, but what we'll see is that oftentimes a parameter is a number that is not really possible to know because you have to have access to the entire population to compute a parameter. A statistic is a number that we can know because it's based off of the data from a sample, right? Which we actually can analyze the data from the sample, right? So if ideally though, we would like a computed statistic to be as close as possible to the parameter from that population, right? Because we're using it to make a prediction. And so we'll explore some methods for increasing the likelihood of that happening as we get later on in the class. So that wraps up this section, right? We've defined statistics. We have looked at the difference between a population and a sample. We have explored simple random sampling. We've looked at samples of convenience and discussed when those are acceptable. And then we've defined and looked at the differences between stratified sampling, cluster sampling, systematic sampling, voluntary response sampling. And finally, we wrapped up this section by looking at the difference between a statistic and a parameter. So, thank you.